Hello, everyone, and thank you for listening to our presentation today. My name is Angela Wells, and I am a cloud engineer. I have my partner here with me, Cyril Azubuine, and we're going to present today and also present our some of our demos and projects that we have worked on together. ROS in the fourth industrial revolution. Thank you and enjoy.
Hi, my name is Cyril Azubuine, and I am a STEM advocate who specializes into robotics and drone technology. Due to my demonstrated history in the field of STEM-related programs, I founded IoT Lab, a platform where kids, teenagers, and even adults get to learn cutting-edge technology skills. These skills are going to be used to help them thrive in the future, and these skills are skills for the fourth industrial revolution. But in today's slide, I'm going to be sharing us tip on how to use ROS in the 4IR. So let's learn how to use ROS in the fourth industrial revolution. Our teamwork. So recently, my colleague and I worked together in using computer vision to not only identify human, but also to recognize human. So when you look at this picture below, you see we have friends and family that we're able to identify as it shows the caption underneath the bounding box around the face. So the algorithm we use here, it's the simple algorithm that used by face recognition experts using computer vision, and it was done using OpenCV library, face recognition library, and also this algorithm uses the Paula-Jones algorithm. We were able to use this for a simple project, but we intend to also use it for security programs in future.
Today we're going to talk about what is ROS, ROS versus ROS 2, the ROS community, the host platforms for ROS for Windows, Linux, and Mac, ROS with Dockers, ROS simulation platform, ROS applications in real worlds, and also we're going to share some of our demos with you. What is ROS? ROS stands for Robot Operating System, and it's more like an environment. What I have learned and from my experience with ROS is the big strength of ROS is this ability of connecting nodes together. And let me share what I'm talking about with connecting nodes. Nodes are pieces of software that can be written in C++ and Python, and that is one of my favorites. Also, with nodes, they can take care of a small subset of tasks. For example, like reading a sensor or just controlling a server. Those nodes connect together. What does this mean? Nodes have information to share, and it will share the information using, like, say, for instance, a topic. And if another node is like interested in that topic of information, it subscribes to that topic and reads the information. Um, it reads the information. So, there are multiple versions of ROS. There is ROS 1 and 2. We're going to discuss in our presentation and also let you see some of our demos. Most ROS 1 versus ROS 2. Most ROS software is free, it's open source, and it's free to use. I remember one of my projects I had to use. It was migrating. I had to migrate a package from Rolling to Galactic, and with using that package, I had to use a tool that move and release repositories into the organization that was controlled by the ROS team. And so, what was involved when I was using that tool was the YAML files. This one of the tools I had to use um, for the release version. The ROS community, this is an excellent platform to use where if you have any like ROS projects or questions that you need help with, this is an excellent platform to use, and really it helps resolve the issues, and especially when you're new like myself, and I definitely use it all the time. Host platforms for ROS. One of my projects I was assigned, um, the objective was to improve an add-on ROS distro to support and to allow the add-on distribution to be named differently from their base distribution. And some of my steps, what I was using, I using the Windows host system, and I was updating the ROS stations to the latest version of dashing. Uh, Import dash packages from the ROS repositories. Um, with this, I had to open a pull request for implementing ROS and the ROS distro support for the updates. And also, finally, I had to redeploy and add a ROS distro and update an add-on ROS distro documentation. ROS with Dockers and virtual machines and Windows subsystems and Linux. Dockers, this allows one to run ROS packages into a container on a host operating system. With this, storage and memory spaces are not shared. Virtual machines, this allows one to run another operation system on an already existing operating system by sharing resources like a hard drive space and RAM. Windows subsystem, Linux for Windows is through the Linux app. I remember when I created, well, I was assigned a project where I had to create a Docker container. It was a ROS infrastructure project I was assigned. So it was one of the ROS build forms. So I created a Docker container based on ROS dashing images. And this is where I created my ROS2 packages, installing ROS dashing with Ubuntu and Debian.
Talking about ROS terminologies. So, a typical ROS platform consists of publisher and the subscriber. So, in this case, you have what we call talkers and listeners. Now, you can have a sensor that talks or that gives publishes signal. Then you have an actuator that listens or that subscribes to the signal being published. So in ROS, you have to get used to these terms. We have ROS services. We have ROS topic, which consists of namespaces. Then we also use some words like SLAM, which is simultaneous localization and mapping. It's a platform that allows your robot to move in a particular path and maybe track itself and come back to that path. So we also have ROS packages, which are a bunch of ROS modules that you can interface with your ROS robot. Then others can be ROS Run, ROS Core, and ROS Node. Mind you, in ROS, there are several nodes you can use to your ROS simulation platform. So aside tools and packages, ROS has simulator environments so you could test run your robot before bringing down the robot into the real world. So we have the turtle sim, which is for 2D. Then we also have Gazebo, which was used in ROS 1, and the Ignition, which is currently being implemented in ROS 2. This platform allows you to test run your robot and also to carry out some simulation on a 3D platform. Then we also have ROS Vis. This allows you to visualize your sensor signal data. And we also have simulation like RQT. These are actually used for analysis and to carry out some other computations. ROS application in real world. So recent years, ROS has been used for making self-driving vehicles like delivery vehicles, and also some ROS programs can also be used for drones in water and also in air. Basically, we have companies like Zoox, Waymo, they actually use the initial measuring unit device such as the LiDAR, the radar, and also the sonar. When all these modules are integrated in cars, they could be used for self-driving vehicles because they have the ability to detect obstacles, to measure the environment, and also with the integration of cameras, they could use computer vision to also analyze and recognize paths, lines, and also humans on the road. Our demo. So in this slide, we are going to give two descriptions of a ROS based and a non-ROS based robot. Now, we came up with a non-ROS based robot which uses Arduino, the driver motors, and also the drivers with the batteries. Then, at this corner, which is my left, I have a ROS based robot which uses Raspberry Pi, and it was also integrated with ROS to measure the value of the sensors and also to give feedback on real time to the controller. So I'm gonna give us a video demo that explains all this, and we see how we could compare a ROS based robot and why we should consider using a ROS based robot more than the non-ROS based robot. In real world, it's really advisable. Hi, so today I want to introduce you to my obstacle avoidance robot. Now let me tell you what makes up this robot. So the robot is made up of just about 6 parts. Now they are as follows. So we have the two DC gear models. So this is actually the DC gear models that I'm going to be working with. Then I have the L298N motor driver. Then I have the Arduino, which is underneath this breadboard shield. Alright, so this is the breadboard shield and the Arduino is just underneath this. Then I have my battery slot. So this is a lithium ion battery, and it's about 2S, which is 3.7 on nominal charge, then 4.2 fully charged. So I'm having about 8.4 volts here. Alright, so this lithium ion battery is going to be supplying current into this whole robot, this robot car. Right, then finally I have the sensor in front. So this is the ultrasonic sensor, which is more like the eyes of the robot. All right, so this is more like the eyes of the robot. So it's how does this robot works. So whenever it drive itself, then once it sees an obstacle that is kind of close to it, like say less than 20 cm or 25 cm, it then decides to turn towards this direction. So it checks again if it has obstacles. If it doesn't, then it's keep moving forward. Then it's gonna just drift again whenever it sees an obstacle in front of it. That's just how this robot works. It's not based on ROS, it's just based on embedded C, which is just Arduino language. But you could actually interface ROS into it, which I'm gonna show you in the next session. But then let me just turn the robot for you so you could see what we have underneath as well. So this is just what you have underneath, just the tires. Yeah, so this is the tricycle wheel. So that's just that about the robot. Alright, I hope you enjoy this. Okay, thank you, and bye for now. So at this point the robot is going to drive itself around an obstacle. Then what is making an obstacle, then you're going to be turning around, trying to look for a spot that is more free, and it's going to continue driving past. That's how it works.
The microphone essentially over here. All right, so this sends and this receives, and then after the trigger, shortly after the trigger is set high, the pulse is sent out, and when it's sent out, the echo goes high and echo stays high until it's received back. So you'll see that emulated in the code. All right, so we've got all our code put together and we've got it all plugged into the robot. I'm going to go ahead and start the robot up with all the nodes that we want. So the first one that I'm going to want to set up here is to start up that sensor node. So I'll let that start spinning, and then I'm going to take another prompt and I'm going to start up the robot itself. The robot's going to be listening on that sensor topic to find out how far away it is, and then I'm going to run my Joy node once again on my laptop. Okay, so everything's all put together. I have 3 separate processes running. One on my laptop, that's where my joystick is connected to, and then 2 on my robot, one that's just for the robot sensor, and then one that controls the wheels. All right, so let's see if we can run into things or if our sensor is now working to prevent us from hitting stuff. Okay, so let's see how this performs. We'll take a look first, just simply driving the robot around a little bit. You see that's working out fine. You see I have a computer set up as an obstacle in the middle of the course here. All right, we're going to drive a little bit and see it's working okay. Now I'm going to try and run into that computer. As you see, I'm trying to go full force, doesn't work. I can still twist. That works out fine. I just can't run into it. So there you have it, folks. We've put together our own robot using only open source software. You've learned how to use ROS, the robot operating system, how to control things with your Raspberry Pi, how to add sensors onto your robot, put it all together into an event-driven model. So it's been great having you. I look forward to hearing a lot more about your